class, this video is on topic D9 transformers and the electrical grid. And we're going to talk about how electricity or electrical energy could get from a power plant, such as a hydroelectric power plant, to your home. Just want to review a few previous lessons that connected together that we haven't had a chance to talk about yet. So in the DC motor, it uses an electric current to produce a magnetic field in a coil. So starting from a battery, starting from electrical energy, and the concepts of electromagnetism that we've discussed, we can cause rotation, and through the components, we can cause continuous rotation. It's really, the star is the split ring commutator that allows for the rotation to be continuous. And it's electrical energy, because we have a battery or a power source, to kinetic energy or motion, because we've got this armature rotating around continuously. We have recently talked about Lenz's law, which says that when you move a magnet near a coil, there is a current created in the coil, and the direction of the current created in the coil is such that the magnetic field will oppose the movement of this external magnet. So we can make use of Lenz's law to create something called a generator. And this is something that we normally go into a lot more detail, but at a high level, a motor is the opposite of a generator. In the motor, we're turning electrical energy into kinetic, and in a generator, we're turning kinetic energy or motion of a magnet into current. So through Faraday's and Lenz's discoveries from the last video, we've learned that when a magnet is moving, when we move a coil within a magnetic field, or when we move a wire, a conductor in a magnetic field, we can create current in that coil. So if, let's say, water was falling here and constantly falling on this side, rotating this around, that current, which is not connected to a battery or plugged into the wall or anything like that, there's no source of electrical energy in this circuit, it's just a conductor. But when the armature is rotating around, because it's in the presence of the electrical, the external magnetic field, we're going to create a current in this. So you do need to know at a high level that a generator takes kinetic energy or motion and turns it into electrical energy, current. Okay, now let's get to the real heart of topic D7, which is transformers and the electrical grid. So we do have to review Faraday's ring. So if you recall, a current in the primary coil, which is connected to a battery and has loops around this soft iron ring, this primary coil is going to create a magnetic field in the ring. And this changing magnetic field induces a current in the second circuit. So the secondary circuit that is not connected to a battery or a power supply, we will be able to detect a current in a galvanometer. And now we're going to extend this Faraday's ring to show this interesting idea of changing the electrical properties of the secondary circuit compared to what you start with. So we might be able to start with a 9-volt battery and end up with 18 volts on this side. And this is how a transformer works, by changing the relative number of loops on the primary circuit and the secondary circuit. So a transformer is an electromagnetic device that can raise or lower the voltage. If it raises the voltage, we call it a step-up transformer. If it lowers the voltage, we step down. So going back to our picture of the electrical grid, where we have, if we notice the voltage of the electricity that is generated at the power plant. So at the power plant, we're taking the motion of the falling water and the rotating battery to turn it into electrical current, and that electrical current has 20,000 kilovolts, or sorry, 20,000 volts or 20 kilovolts. So 20 kilovolts is way more voltage than you would want to be delivered to your home. We want 240 volts. So there is a series of step up or step down transformers used along the way to convert the voltage. So at first we step up the voltage to up to 500 kilovolts. Then we step it down to 115. Then we just step it down to 44, then to 4 kilovolts, and then not 4,000 volts, but down all the way to 240 volts or 120 volts, which is the voltage of the outlets in your house. So 240 volts would be the electrical outlet of where appliances go. So if you notice that if you were to unplug your fridge, don't try this at home, but if you were to unplug your fridge, you would see a slightly different style outlet than if you unplug your toaster. So small appliances have 120 volts. Those are most of the appliances that you would see. And then maybe if you were in the middle of a move or a renovation, you might see the outlets that your dishwasher and your laundry machine and your fridge get plugged into. So the idea is that we may want to change the voltage so we don't just have one circuit all the way from the power plant to your home. We have these intermediate circuits and we change the voltage along the way. And we do that using the transformers. So like I was saying, if you have if you want a higher voltage on the second one, it's called a step up transformer. And if you want a lower voltage on the secondary coil, then it's called a step down. So if we go from a high number of coil loops or turns or windings to a low number, that's called a step down transformer. So it's kind of easy to remember that the voltage goes down and the number of loops goes down, and it's called step down transformer. And then the voltage goes up when you have a higher number of loops on the second one. So the number of loops goes up, the voltage goes up to the second one. So that's a step up transformer. So if we take a look at some of the numbers, so let's say we have 100 volts electrical current and we want to turn it into 400 volts. We could increase the number of turns by 4. So that's 4 times bigger voltage. So the number of turns increases by 4. If we have 1,000 volts and we want to turn that to 200 volts, so that's 5 times smaller, we take whatever number of turns we have on the primary coil and divide it by 5. So 5 times smaller voltage, 5 times smaller turns. 4 times bigger voltage, 4 times more turns. Now look at what happens to the current. So the current, while 100 volts was multiplied by 4 to get the new voltage, the current was divided by 4. So the number of volts and the number of turns are proportional, but current is inversely proportional. So the trend of the current from one side to the other is the opposite of what you'd see for the voltage. So 1,000 volts turning into 200 volts, you divide by 5. The current you'd have to multiply by 5. So we have a mathematical relationship to help you work on these problems. At the end of the day, it's just ratios. So the number of, we have capital N being the number of turns. So the number of turns on the secondary side versus the number of turns on the primary side is equal to the ratio of the secondary voltage divided by the primary voltage. But notice it's S over P, but this is flipped. That is not by accident, because remember, when voltage increases by 5 times, current is divided by 5 times. So we do have to remember that they go on opposite sides. This is one of the formulas that is on the exam formula sheet. So let's try an example. We have a transformer used in an adapter for a laptop that has a primary voltage of 120 volts. There are 250 turns in the primary coil and 25 windings in the secondary coil. Calculate the voltage in the secondary coil. So you know when you plug in your laptop, there's sort of that rectangular piece. And you'd say, oh, do you have the adapter? I don't know if that's maybe a dinosaur way to say it, but anyways, it is called an adapter because it actually adapts the voltage from the voltage that you plug in the wall to the voltage that is safe for your laptop. So when we plug into the wall, we have 120 volts, but in the computer, we want less than that. So in this transformer, in that adapter, we start with 250 turns on one side and 25 turns on the other side. So that is how many times less? So let's write this up. You're always going to start with a diagram. So you're going to start, I just draw a rectangle inside a rectangle to show kind of like Faraday's ring. So on one side, we have 250 loops. I didn't count 250 loops, just do a whole bunch of loops, and then 25 loops on the other side. So you have to do 10 times less. And then on the primary side, it's 120 volts, and we want to calculate how many volts are on the secondary side. So we have NP and NS and VP, and we want to solve for VS. So writing this ratio, we want to isolate for VS. VS is equal to VP, so we cross multiply, VP times NS over NP. And we get VS is 12 volts. And that would be appropriate for the number of sig figs as well, because there's 2 sig figs in this number. The number of turns is not so much, it's not a measured number, so we don't look to it for judging the significant figures. It's exact. It's like you have 250.0000 turns. It's exactly a certain counted number of turns. So that's the first example. Let's try another one. So we have 125 turns in the primary side and 1800 turns in the secondary side. Is this a step up or a step down transformer? So pause this video right now and see if you can think of, if you can recall what we said about a step up and step down transformer. So we step up the voltage. We step up the number of turns. So we know that it's a step up of the voltage because there is a greater number of turns on the secondary side. And then if we have 3 kilowatts of power that are input at 250 volts, what are the voltage and current outputs of the secondary side of the transformer? Oh dear, I think I put this in the wrong order. We have to get to the power conservation formula and we'll come back to that question. So what is conserved from one side to another? Well, we know that there is a compromise. So you get more voltage, but you'll get less current. So you can't just create energy. This comes from the law of conservation of energy. So the energy in equals energy out, and we know that energy over time is power. Therefore, the power on the input side is equal to the power on the output side. And power, and one equation for power is voltage times current. So this is actually a new equation in these videos. So power is voltage times current on one side. Power is voltage times current on the other side. And that's actually how we get the ratio of VS over VP equals IP over IS. And sorry, back to the example. So we've got a certain amount of power, we've input the voltage. Okay, so let's go to draw the diagram first. So we draw the diagram of going from 125 loops to 1800 loops. We have those givens. We also know that we start off with 250 volts. So how do you get the voltage on the secondary side? We don't need that power rating at all at first. So our secondary side voltage is the primary side voltage times the secondary number over the primary number. So our secondary side has 3600 volts, and that's our final answer for that part, but it also says what is the current output. So one way is just to solve it using that current ratio. So you would do NS over NP equals IP over IS, and that's the perfect way to solve for it. Here's another option, just in case you want to learn as many different ways to solve these problems as possible for moving on. Power is voltage times current, and we have the power and the voltage on the primary side, so we can calculate that it's 12 amps. Here's the other way to solve for it. We also, oh dear. We should get the same number. Okay, taking a look at this question, we get 12 amps for the primary current. You have to use power equals voltage times current to solve for the primary current, then what's being asked is the secondary current. So we actually have to use both the power equation and the ratio, the relationship of the ratio between the number of loops and current. So we get that the secondary current is 0.83 amps, which is as many times smaller compared to 12 as 1800 is bigger than 125. So 1800 divided by 125 is, so we're 14.4 times bigger on the number of loops. Therefore, the current has to be 14.4 times smaller. Okay, so let's talk about transmitting electricity. So alternating current, recall that alternating current is when the direction of the electrons change a certain number of times per second. So when we actually plug things into an electrical outlet, 60 times per second, the electrons are changing their direction. So they're oscillating back and forth. And our AC electricity would have a significant amount of power loss. If it was DC current, it would have a significant power loss. So AC electricity is used because it minimizes power loss. So there's a famous debate about whether, if you think about before all these power lines to houses were set up, the infrastructure hadn't been set up. So someone had to decide, are we going to design our cities based on DC and AC? And there was a dispute between two famous scientists about which was the correct, like the best decision for building a city. And ultimately AC won. And it's because a significant amount of power generated at power plants can be lost due to thermal energy losses as large currents pass through the transmission of wires if we were using DC. So there would be a lot of power loss. So we use AC. Recall that power is voltage times current, or power is current squared times R. Those are the two equations that showed up in the homework, so you had to read the tutorial. These equations are used to calculate the power loss in a transmission wire. I'm going to give you a heads up. This is true, but it's the potential difference across the wire. We're hardly ever given the potential difference across the wire from one point where you're starting the wire line to the end. So this is the equation that we're going to be using for power loss. So step-up transformers at plants are used to increase voltage and decrease the current for transmission. However, high voltages would be very difficult for the end user. Step-down transformers are used throughout the grid to bring voltages down to levels that can be used in homes. So we step up for transmission because it minimizes power loss, and then we step down just before the house because you want to bring voltages down to a safe level. And this is just restating that. We're stepping up to a high voltage for transmission, then we step down to a lower voltage by end users. So if you take a look at the diagram again, here is the hydroelectric plant. The water, which is high up, has gravitational potential energy. It is falling. It is turning the arm of the generator, so that's kinetic energy. That kinetic energy through the generator is turned into electrical energy, and that electrical energy it's 12,000 volts when it starts off. We want to step it up to 500 for transmission so that there's not there are minimal power losses, because the thing that affects power loss a lot is I, because it is squared. So we want to minimize power loss. When you step up the voltage, you minimize current. So you minimize current, you minimize the power loss. And then when we get just before the house, we step it down to 240, or, well, it's actually a series of stepping it down from the very high 500. So let's try an example of power loss. So a generator produces 300 megawatts. Mega means times 10 to the 6 of power at a current of 30 kiloamps. Kilo means times 10 to the 3, which travels through a transmission wire of resistance 0.1 ohms. Calculate how much power is transformed into unusable energy, or thermal. So we are starting off, this is not like an official diagram, but I think it does help. So we have a long wire, and we start off with 300 megawatts of power, 30 kiloamps. And you want as much of that energy to reach the end as possible. Remember, power is energy per second. So if we think of taking a photo where we're looking at just 1 second at a snapshot in time, then you can think of that as energy. We've got energy going in, electrical energy, and we might have energy lost, like, for example, thermal energy. And we want as much energy to go out as possible. The power loss is current squared, 30,000 amps squared, times 0.1 ohms. So we have 9 times 10 to the 6 watts lost out of, and you could think of that as joules per second. So in 1 second, 9 million joules are lost for every 300 million joules that are sent. And the efficiency of that is, well, we can get the energy out by doing 300 million minus 9 million. So we get 291 million. And we're going to divide it by the energy in. Or you could use power out over power in, but I think it's more proper with the energy efficiency equation to use energy. So 300 megajoules is in the denominator, and that's 97%. So that's not bad, but 3% is a lot when you're talking about in the order of mega. So that's actually a lot of loss. If part B says now we're going to use a transformer. So now we're going to use a transformer, calculate the new power loss. So with the transformer, it steps up the voltage, it lowers the current. So remember, we use the current value in our power loss equation, so we get it down to 3,000 amps, which is 10 times smaller. So now we only have 9 times 10 to the 5 instead of times 10 to the 6 lost. So now when we do our efficiency equation, we get 99.7%, which is obviously better than 97%. So now it's time for you to practice questions on transformers and the electrical grid. So please make sure to submit this exit ticket and submit these practice questions when you're done. Have a great day.